Good morning. Welcome to the final edition of Chemistry on the Fly with Mr. F. Today we're going to talk about 7.50 and it's going to be the chemistry of fats. Now we've learned earlier that there's several types of foods that we get from our food and drink, and they're carbohydrates, proteins, and fats or lipids. So we're going to talk about fats or lipids today. So let's look at couple things about fats. So the fats, let's look at the foods that fats are in. So we're going to get it from milk and cheese, meats, butter, avocados, oils, or olives, fried foods, and oils. Some of the types of fats that we're going to see today, we're going to talk about saturated fats, monounsaturated fats, polyunsaturated fats, and the trans fats. Now, before we get too far, back in the 1960s, there was a movie called The Good, the Bad, and the Ugly. It had Clint Eastwood in it. And it really was a medium movie. But that's what we're going to talk about today. We're going to classify our fats as the good, the bad, and the ugly. Now, a little bit before that, though, in the 1950s, scientists decided that all fats were ugly. All fats were bad. So there was a big push to get fats out of our diets. And in turn, what happened is we exchanged fats, which were bad or ugly, for carbs. And I think, this is my personal opinion, that is where our epidemic of obesity has come from. That we realized, at least the scientists thought, that all fats were bad back in the 1950s. Well, we'll find out that there are actually some good fats, there are some bad fats, and there certainly are some ugly fats. So, here's one of the things. Here's some of the roles that fats do have. They store energy for future use. They send signals, and they hold cells together. Now, a couple other things that are important with fats that why we need them is that some vitamins like vitamin A, D, and E, I believe, all are fat soluble, which means that we wouldn't be able to get them into our bodies and store them in our bodies and use them if we didn't have fat in our bodies. And one of the things that we'll realize a little bit later is that they're insoluble in water. That's just a general thing about fats, but we'll explain why that happens a little bit later. Now, one of the things that I think scientists back then realized is that fats actually have 9 calories per gram. So when they store their energy, their potential energy, they store it. They have 9 calories per gram. So if I want to cut down my calories, all I have to do is reduce the number of fats, because it's more than double the amount of calories that carbs or proteins have. So I guess the premise was good, to get rid of fats, but in turn what the food industry did, was they increased the amount of carbs. And so I think that overall they probably have more calories in them than they did before we removed the fats. All right, so let's look at the idea. Fat's going to have long chains of carbons attached to a carboxyl group or a glycerol group, and we'll see that in a second. So let's look at the first group. So the first group is called saturated fats, and we're going to start with looking at the structure of it. So the first thing we're going to start with is a carboxyl group. So there's our carboxyl group. And then we're going to have a long chain of single-bonded carbons saturated with hydrogens. So we talk about the idea of saturated fats. Well, they're saturated because the carbons are all surrounded by our hydrogens. So we can see that here, that the carbons in the center, the carbon chain, are saturated with hydrogens. And then the last part of it, and this is what makes it insoluble in water, is that it has a methyl group. And if you remember from our methyl group, they are going to be nonpolar, and nonpolar is not attracted to water. So this is going to make it hydrophobic, which means it hates water. So that's why fats are insoluble in water. This particular one is called palmitic acid. And you can see the formula there, C16H32 oxygens 2. So this is a typical saturated fat. So let's look at some of the characteristics of saturated fats. First of all, they have a linear formation. Now the linear formation, now I'm showing it very linear here in a two-dimensional way, but they are still much more linear than other fats, and we'll see why in a second. And this means that they're stackable. Now stackable is going to be important because this is going to give them the ability to stack on top of each other, which gives them the ability to stay as solid at room temperature. And we'll find out that solid at room temperature actually lasts longer on a shelf life, so that is a good property to have. And then they're going to have higher melting points, which is good. And then they're going to be found in pork, beef, milk, cheese, eggs, and butter. Now on our scale, on the healthy scale, the good, the bad, and the ugly, I'm thinking these are not going to necessarily be on the good side, but these are going to be on the bad side. We want to keep saturated fats at a limited quantity. All right, and you can see that they're saturated again because they have hydrogens all across the carbons. Now we're going to talk about the next one, and the next one we'll see why we changed to unsaturated, and we'll see what unsaturated means in a second. Now we'll take this big word monounsaturated, and you can see mono means one or single, and unsaturated, and we'll figure out what that means in a second. So here's our structure. Again, we're going to start with a carboxyl group. We're going to then have some chains of single bonded carbons started or saturated with hydrogens. Now here's where our difference comes in. Now we're going to have one double bonded carbon. Now if we look at this, we see that our double bond with carbon, we remember carbons have 4 bonds available. Well, when they double bond, they have 1 less available for the hydrogen. So we're going to have 2 less hydrogens when I have two double bonds or a double bonded carbon. And we'll see what's going to happen in a second when I add the rest of my carbons in here with my hydrogens. Okay, we can see that I have a bent molecule, and we can see that I have this gap in here where this is where I get the unsaturated. In the first one, in the saturated, we noticed that we had 2 rows of hydrogens completely saturating the carbons, but here I have a gap here, and this gap is what makes it unsaturated. And just like the other one, we're going to have our methyl group, which again keeps us hydrophobic, not liking water. All right, now let's look at some of the characteristics. The bent formation means that it's not going to be stackable. It's going to then have to be liquid at room temperature. It's going to have a low melting point. It's going to be found in plant oils, avocados, nuts, and seeds. And on our healthy scale, we're actually going to call this one a good one. So this one's going to be a good fat. Now this one's still got to be a little careful. We want to make sure that we don't overdo our fats. This one's called omega-9, and this is a good fat. In our scale, good, bad, and ugly. But we still want to keep limited quantities. All right, so let's look at our next one. The next one's going to be a polyunsaturated fat. So here we go with our structure. Okay, again, we're going to start off with the similar look as our last one, but in this case we have poly. Now poly means many, so this time we're going to have multiple double bonds, and we can see that here. So here's our breaks in our action. So in this case we have 3 breaks in the bonds, or in the 3 double bonds, which means that I have 3 breaks in the hydrogens. And just like before, we're going to have our methyl group at the end. Now this is going to give us, this happens to be omega-3, and this one is a very good fatty acid, or acid, not fatty acid, it's going to be a good fat, and we'll see that in a second. So let's look at some of the characteristics. Okay, this is again non-stackable, so this is definitely going to be a liquid at room temperature. It's going to have a low melting point, and it's found in flaxseed, walnuts, salmon, and tuna. And again, on our healthy scale, this one's actually going to get the good. And we still, one of the things that we do want to realize, or we have realized, is that omega-3, they call them fatty acids or fats, are going to be good for limiting inflammation. Now, scientists have beginning to realize that inflammation is the cause of a lot of problems, especially in older people. So we want to try to limit the amount of inflammation in our body as much as possible, and omega-3s can certainly help that. So let's look at a different one. I don't want to lump all of the polyunsaturated fats as good, because this one's kind of a bad one. This one's called omega-6, and it has some similar characteristics. In fact, it has the same characteristics as our last one. But this one's actually going to be, we're going to consider this a bad one. This one actually does the exact opposite of omega-3. This one's called omega-6, and this one actually promotes inflammation. So this one kind of does the opposite effect. So I don't want you to get the idea that polyunsaturated fats are good, because some of them are really not so good. So let's look at one of the things that's, so far we've looked at some good ones and some bad ones. We haven't really talked about any ugly ones yet. So let's talk about what makes something good or bad versus ugly. All right, so here's one of the things that we've seen so far. We have a carbon with a double bond, and we have the two hydrogens, and we're missing the two hydrogens on the bottom in our bond here. And this is called a cis. Now cis, C-I-S, it means the same side. Okay, now let's look at, you can see our hydrogens are on the same side here. Now let's look at the opposite of this, a cis. This is called a trans. Now, this is where the idea of trans fats come from, and that's going to be our ugly ones. We'll talk about those in a second. But trans comes from the word, or means across. So when we look at the double bond here, I still have the double bond with carbon, and I still have two less hydrogens, but my hydrogens are now across from each other and not necessarily in line. So what's going on here? So first of all, I have the natural is that my cis bonds, double bonds, and then on my trans, they're actually mostly not natural. Now, when I say non-natural, I mean that they're actually processed, man-made, or man has processed them so that they're not natural anymore. And what this happens, let's finish this little thought here. These are the natural ones, are our good and our bad ones, again in our 3 good, bad, and ugly scale. And then our trans, these are definitely going to be the ugly ones. Now, let's explain how this man has processed these. Now, what happens is that you have the food processing industry back in the 1950s started to do more processed foods, and they needed a fat to process them, whether it's for frying or whatever it is. They needed that, and they wanted to make it less expensive, and they also wanted to make it last longer on the shelf, since we don't have we have a lot of things that they say Twinkies last forever because they have a lot of processed fats in them. So what scientists did is they found a process called hydrogenization. Excuse me, that's a tough one to say. And what happens is they take a inexpensive fat like cottonseed oil, and they pump it with hydrogen gas. And the hydrogen gas takes a bent molecule with a cis bonds and pumps extra hydrogens in it, and then takes some of those cis's away and actually causes them to become trans bonds. And that trans is what we'll see in a second is really what causes us so much trouble. So let's take a look at what a trans fat's going to look like. So here's our structure. Again, very similar to, we're going to start with a carboxyl group. We're going to have a bunch of single bonded chains, and then here's where we become different. We add one or more trans double bonds. So you can see, I'm just going to show you one trans here. You can see where the hydrogens are across from each other, and then you can see I added a bunch of other carbons that are single bonded. And then at the end, I did add a methyl group. So again, this one's called translinoleic acid. Now, some of the characteristics that this added was it's now a semi-linear formation. So that means that it's stackable. Now, stackable means that it's going to be solid or semi-solid at room temperature. And this is one of the things that the food manufacturers wanted to achieve. They wanted it to be solid at room temperature. Again, part of that is that it will make it last longer on the shelf. It has a higher melting point, and it's found in fried foods, bakery items, and in chips and other things like that. So the fried foods, that's where we get our fried chicken and that kind of stuff. That is actually going to be fried in an oil that, as they use it, it gets more and more trans fats in it. So what they're trying to find is a way to get rid of the trans fats. Now, in bakery items use trans fats so that they could make things fluffier and flakier and typically taste better, to at least to our taste buds. And then in chips, they use them to as a cheap way to fry their potato chips or their corn chips or whatever. And as healthy wise, these are going to get the ugly. We definitely need to avoid these trans fats. Now, the trans fats, the FDA recently, in about 2018, banned all trans fats in processed foods. Now, that's a good thing because trans fats are bad for us. They're bad for our heart, they're bad for our arteries. So they are really bad for us. So in processed foods, we're supposed to get rid of all of our trans fats. Now, this has certainly, the food manufacturers have certainly changed, and they are, I guess, as always, they try to find a little bit of a loophole in the system. So I don't really want to pick on Krispy Kreme. I've had my share of Krispy Kreme donuts, but you can see on their label, their nutrition label, that it actually says that it has 0 trans fats, which is good. Now, most manufacturers are pushing, because the FDA said so, to have 0 trans fats. Now, we have to be careful when we do this, though. Just because they have 0 trans fats, the FDA did have a little bit of a loophole. They said that per serving, they can have up to 0.5 grams of trans fats and still say they have 0 trans fats. So we've got to be a little bit more cautious. Just because something says 0 trans fats, we have to look for a key word, kind of a code word in the ingredients. And the code word is actually going to be partially hydrogenated. And this is, I guess, the bad word, because this says that they still are using processed oils to fry or to make their, in this case, donuts. But this shows up in corn chips and other places as well. So we still have to, even though they say 0 trans fats, we still have to watch the ingredients. And if they say partially hydrogenated oil, in this case it says soybean oil, and if we look at the next line below, it says partially hydrogenated cottonseed oil. So we've got to be very careful of what kind of oils that they're using in the process. So again, partially hydrogenated is really the bad word that we want to keep. That's what really is making this an ugly oil when we talk about trans fats. All right, so let's look at how we talk about our storage. Now, when we have extra calories, we store them in something called triglycerides. Now, this is where we have extra calories. Now, it's not necessarily fat calories. It's going to be any calories. So when we get a protein or a carb, we're going to store it in fats. And it's going to be stored in triglycerides. And you'll see how that looks in a second. But these are going to be stored in our blood and then in our fat cells. Okay, and then the objective here is to release them later and use them for energy. Now, what's happened is that as a society, we've taken in more calories than we're actually using. If you probably didn't notice, but that one donut had 250 calories to do that, and that's probably to run maybe 3 miles to get rid of 250 calories. So that's quite a bit of energy that we have to put out just to take care of that one donut that we just ate. Okay, so we have to be careful of how many calories we take in versus how many calories we use. But again, we're looking at how does our body store this. Now, it would be not so good if we just had to eat or had carbohydrates and we would just eat them and we would use that energy right away and then we wouldn't have anything. So we'd almost have to eat all day long. Now, our bodies certainly don't do that. I mean, we have to actually not eat all day long. We don't have time to do that. And then back in the older days when we had to hunt, um, we certainly didn't eat all the time. So our bodies had to develop a way to actually store these energy for future use. And again, this is what it's going to look like in a triglycerides. So we have a glycerol functional group, and then in this case, we're going to add 3 fats to it. And you can see the fats. We have the carboxyl group with the chains of carbons, and then a methyl group at the end. So even triglycerides are also going to be hydrophobic because they have the methyl groups at the end. But this is how we're going to store it. And then we would just basically use this fat as we needed it later on for energy. Well, we're getting close to the end here. Eat your broccoli, as I've been saying the last couple times. Broccoli has 0 trans fats, so you don't have to worry about it. It's going to be good for you. Stay safe and strong. And as always, this is Chemistry on the Fly with Mr. F, and have a great day.